Welcome. In this lesson, we are going to take a look at the idea behind trees and forming spanning trees out of graphs. So a tree is just a special type of graph, and it's one that is connected and has no cycles. Connected means that you can get from any vertex to any other vertex, and no cycles means that I should not be able to start and end at the same vertex by taking a different path to get back. So the common type of tree structures that we see are in things like file directories, where you have some root directory up here, and then maybe, I don't know, you have your pictures here in this folder, and maybe here you have your Word documents, and then maybe over here you have some miscellaneous files. And then within each of these folders, maybe you have some, these are just your files, or maybe this one has more folders here, and maybe these have some files and another folder here. And so this process can continue. Now you notice that I cannot start at any vertex and get back to that same vertex without hitting other vertices that I've already visited. So for example, if I took this path here, and then this path here and this path here, the only way to get back would be to revisit the existing vertices. If, however, I somehow close the loop here, for instance, if I put let me actually write this on a separate graph so that we have a comparison. Okay, so here in this particular graph, if all I did was connected two vertices, like say this one and this one, and these should all be vertices here as well. Some of these are files, some of these are folders, and in this case where I've added the extra connection here, you now see that I've created a cycle or a possibility for a cycle. So I can start at this vertex and I can get back to that vertex by traversing a loop. So this is not a tree. This is a tree. Okay, and so a tree should be able to be organized in this hierarchical way where you have basically some sort of root node, or you could have multiple root nodes. Like perhaps there are two root nodes that continue to span out. And this particular tree starts to reflect what we call a binary tree. A binary tree is one where the number of divergent paths is always 2 at any vertex, except for perhaps the last vertex. So these are, this would also be an example of a tree, but notice that this one's not connected. So in order for it to be a tree, we would have to make it connected, which means having a root node up here would make it so that now these two halves are connected, and this is a tree. Another place where you commonly see trees is in the way that a computer keeps track of order of operations for arithmetic. And we won't go into that here, but trees are extremely important and extremely valuable in computer science. So here's kind of an example to motivate why we would want to use trees. Suppose we are planning a telephone network for an underdeveloped area with 5 isolated towns. We have U, V, W, X, and Y, and here we see, that's better, there's our X node. So we have these 5 underdeveloped, we have these 5 isolated towns. We can build a phone line between any 2 towns, but it is not necessary to have a direct line, as it suffices for one town to connect to any town via some path. So basically, we don't need all these connections here because we would be putting in a lot of phone lines when, if it's possible to connect U to X via some other path, then we should probably do it that way. The current proposal is represented by the following adjacency list, where the vertices are towns and an adjacency represents a line of communication. So basically, if we were to draw this graph, what we would see is that vertex U, V, W, Y, and maybe I'll put X over here. So U, V, W, Y, and X. And the way things currently stand is we see that U is connected to all 4 other vertices, V, W, X, and Y. We see that V is connected to U, W, X, and Y. So U, W, X, and Y. W is connected to U, V, X, and Y. So U, V, X, and Y. Y is connected to U, V, W, and X. And X is connected to all 4 vertices as well, and we already have those edges built in there now. So make this graph into a tree and explain why it satisfies the constraint posed with minimal infrastructure. So if we design this into a tree, we're going to still have a graph that is connected, because that's the requirement of a tree. But what we're going to do is we're going to delete edges to avoid redundancy. So for example, to connect U to X, I don't need a direct path there. I could actually take that edge and remove it, and I can still send signals over to X via a number of different paths. Similarly, U and Y are connected directly, but I don't need that direct connection. I can connect U to W to Y. So I can remove that one. And in fact, if I also remove this one here, you see that it's still possible to have a line of communication. Also, I probably don't need a direct communication from W to X, because I can still have one phone line that goes from W all the way to X via Y. And then also I could probably remove this one, because I can still get a signal from Y to V via X or via this path. And here I can see that I can get a message to U from U to W, but I have another way to get a message from U to W as well. So I probably don't need both of those paths. And at this point, if I were to delete any other edges, I would get a disconnected graph. For example, if I remove that one, now there is no way to communicate with town U, and therefore I do need a phone line that goes from U to V. And I cannot remove any more of these edges because I will not have a tree. And you can actually see the hierarchy here. If you draw this vertically as X is here, X connects to U to V and Y, which connect to U and W respectively. So you can see we've created a tree out of a graph. And this in general could be kind of complex to do, because here we were just eyeballing it. And by the way, this configuration is not unique. We could have, for example, left this edge and have deleted, say, any one of these edges now at this point. If we had deleted that edge, then still it's possible to make that work. So this is not a unique way to turn this into a tree. And at this point, we just need to build 1, 2, 3, 4 separate phone lines to connect all the towns. Another thing to be thinking about is if these edges were weighted, if there were actually distances here, then we would want to minimize the distance, maybe the overall distance. But that's a different kind of algorithm altogether. So other types of problems may not be solved by this approach. So before we get into what we're talking about here, which is to take a connected graph and convert it into a tree, this is actually called a spanning tree. And a spanning tree is a graph that contains all the original vertices of the graph. So it contains all original vertices. And we'll just call this graph G. Contains all original vertices of G, except that now it's a tree. right? So we've converted a graph into a tree. This wasn't a tree because you can see there are many, many cycles here that you can take, but now there's no cycle. We've removed that possibility. Here are some interesting things that we want to think about when we talk about trees. In a tree, there is exactly one simple path from vertex U to any vertex V, meaning there's only one way to get from any vertex to any other vertex. So if I just draw a tree here, just a real simple one, and maybe I'll branch this out a little more, and maybe I'll just take this one down like so. This is a tree. There's no cycles in here. It's connected. And so if I, for example, pick vertex A, and maybe I call this vertex B down here, then clearly there's only one way you can get from A to B. There's only one such path. There's no other way to get to B that wouldn't require traversing one of the edges more than once. So I could technically go down here and then back up to B, but that's not a simple path. In a tree with more than one vertex, there are at least two vertices of degree 1. So first of all, the thing to note here is that A, the root of your tree, is going to have a degree of 1 because that has to branch out from that doesn't have a degree of 1. I apologize. That has a degree of 2. But if you think about a graph, if I start making a tree, then this vertex will either have, potentially 1. And in this case, you see that both of these vertices have degree 1. Now, if I add another edge and another vertex in this tree, so this is still a tree, now you can see I have 2 vertices of degree 1. No longer is my root of degree 1, but my 2 branches here are of degree 1. And now if I even further branch this out at this point, you can see that now I have 3 vertices with degree 1. And so this will always be a true statement. A tree with n vertices has exactly n minus 1 edges. So if you look at this graph here, you can see this has n equals 1, 2, 3, 4, 5 vertices, and it has 1, 2, 3, 4 edges. Now that has to be true because if you add another edge in here, like there, then you're making this graph into you're removing the non-cyclical nature of the graph, and you're creating a cycle. It doesn't matter which 2 vertices I connect, I'm now creating a cycle in there, and so this statement must be true. Removing an edge from a tree makes it so that the graph is no longer a tree. Okay, well that makes sense. If I remove an edge, if I remove any edge from here, well, that's no longer a tree. Why not? Well, because a tree has to have no cycles and it has to be connected. So if you remove an edge from a tree, it's not a tree anymore. When an edge is added to a tree, it is no longer a tree. So this is a tree. If I add any one edge, that's going to create a cycle. So otherwise, a cycle is created. If you remove an edge, you are making it disconnected. All right, so here's an example of where we have a graph, and we have an oil company that wants to build a series of pipelines between 6 different storage facilities. Those are given by each of the 6 vertices. The process is expensive and the company wants to construct as few pipelines as possible. The graph shows the facilities, the nodes, and the allowable pipelines. Right now, we're not focused about how long these pipelines are. For all intents and purposes, let's just assume they're all the same length. A spanning tree of a graph G, so this is our graph G here, is a tree containing all the vertices of G. So basically what we're going to do is we're going to convert a graph like we did up here into something that's still a graph by definition, but that now matches the constraints of a tree, that it has no cycles and that it's connected. Now, in order to do this, we could start removing edges one by one, and that would give us, potentially a multitude of different types of trees we could create. There isn't just one spanning tree that we can create. Our task is to form a spanning tree for the pipeline system above. Okay, well, here's a little argument we're going to make. We're going to say for an unweighted graph, forming a spanning tree can be simply reduced to the use of the breadth-first search algorithm, the same algorithm we used for finding the shortest path from one vertex to every other vertex in an unweighted graph. The reasoning is actually quite nice and simple. If there is an edge that connects two vertices that already have shortest paths, as in the graph below, the edge connecting them is not considered as a route for the shortest path and can thus be removed. So if we remove any one of these edges, we're going to have a tree. Now, whenever we do the algorithm for a breadth-first search, remember the first thing that we do is we pick a starting vertex. So depending on which starting vertex you pick, your spanning tree may look different. So let's just say that right now we're going to start at this vertex here. And let's actually label these vertices. We'll call this A, B, C, D, E, and F. I'm going to ignore the labels of the edges for now because we could just describe the edge here as the edge CD. Okay, so let's just say I start at A. So the algorithm has said let's list the vertices that we have already visited. So vertex A. Now the algorithm says, okay, give it its weight. Well, A is a distance of 0 away from itself, and so the starting vertex always gets that label of 0. And that's our value of K. That's K equals 0. So the next thing we do is once we're done with that step, that initialization step, we adjust K to be 1. And this is just a distance counter. So now we look at all the neighbors of this vertex, which are B, C, and D. And B is 1 unit away from A. And it's 1 unit away from A, but its most recent predecessor is A. And C is 1 unit away from A. And D is 1 unit away from A. So now we have to add all these vertices into our set. C, B, and D. It does not matter what order. This is not going to produce a unique tree. But you'll see in a second what we've really done here is we've kept the connection from A to B. We've kept the connection, and I'm sorry, I shouldn't have said C. C is not a neighbor. I apologize. That should have been F, B, and D. So this should be 1 away from A. There we go. So that takes care of those 3 edges. So this should be F. And so now that we're done with all of the neighbors of A, now we increase K to be 2. And remember, we're just trying to think like computers here. So K equals 2. So for F, we want to look at all the neighbors of F. Oh, and that's what I was going to say is that notice that now I only have 3 edges, AB, AD, AF. And now I'm going to look at all the neighbors of F. So F has a neighbor of D, but now that K is 2, I don't want to say that the shortest path to D is 2, A, F, D. That's excessive. I could just connect A to D. So F, the only other neighbor that F has is E, and so that means now E is going to get a label of 2. Most recent predecessor is F. And so now I'm going to add E to the set. F has no other neighbors. I'm going to move to B. Look at B. B has 1 neighbor that hasn't been visited yet. A to D is the shortest distance there. A to B to D would clearly not be shorter. So that C is going to get a label of 2. Most recent predecessor is B. We're done with B. We now move to D. And so we added C to this set now. D has no other neighbors that haven't been already listed. So we're done with D. E has no other neighbors that don't already have distances. And C does not have any neighbors that aren't already labeled. In other words, our list contains all of the vertices, which means now we have shortest paths. Now here's the way you can work this. At the top of your tree, place the vertex that has the lowest K value. So A is up here. And this is for k equals 0. Below, list all of the vertices that have a k value of 1. So that was B, D, and F. So B, D, and F are all immediate neighbors of A. Now, from there, now we are going to look at the next level, which will be for k equals 2, vertices that are 2 units away from A. And those will be vertex C, which its most recent neighbor is B, so this will connect C. And then E, which its most nearest neighbor is F. And we have no other vertices left, and our last label is k equals 2. If this tree were a lot bigger, then we might have to increment k again, but we've already labeled all the vertices, and every vertex can be achieved from any other vertex in at max a walk of length 2. And so you can see that now we have pipelines that connect all the towns. There are no cycles, meaning we don't have any extra edges, and this graph is connected. So what we've essentially done is we've removed every other label. So we've removed that edge right there. We have removed that edge right there. We've removed this edge. We've removed, we've removed this edge here. And I think that's it. A to B, A to D, A to F. B should just connect C. D should not connect anything else, which that means this edge should go as well. Only A and D should be connected together. And then F should only connect to vertex E. E should only connect to F, which only connects to A. And so by removing these 1, 2, 3, 4, 5 edges, we have created a spanning tree that contains all the original vertices of the graph, but contains no cycles and is connected. So using breadth first search is not only a way of finding shortest paths, but it also is a way of creating trees whenever necessary. And so once again down here, if we removed any one of these edges, we could even do the breadth first search algorithm. Let's say we started with our list, which let's say our first vertex was vertex 1. Okay, at that point we could say k equals 0. Okay, the only vertex that will get labeled with this index of 0 with no predecessors is our first vertex. 1 has neighbors of 0 and 2, so now that we've initialized, we set k equal to 1, we increment it by 1, and label all the neighbors of our vertex that's in that set, which are vertices 0 and 2, and those are all both 1 unit away from vertex 1, 1 unit away from vertex 1. And so now we look at all the neighbors we adjust k to be 2. 0 does not have any neighbors that haven't been already taken care of or that don't have labels yet. Vertex 2 already has a label, therefore we visited all the vertices. Everything is labeled, and so now we see that the vertex 1, which is the label of k equals 0, and down here k equals 1, the vertices will be vertex 0 and vertex 2. And so effectively, what we've done is we have deleted this edge right here. Again, there are many ways you could form this tree. This is not a unique process. It depends on what vertex is going to be at the top of your tree for one, and sometimes you have to make a decision as to which vertex you visit next. So a lot of times there are multiple answers for doing this process.